So for this question right here, if it's a fairly simple structure where it has a central point on which you have same groups and lone pairs, you can actually use this table to figure it out because that's just very fast, right? Okay, and so this would then give you your molecular point groups. Now, if it's a more complicated structure, you may have to sit there and figure out using your point group symmetries what type of symmetry it has. Remember that big flow chart? You'd use that flow chart, right? Okay. Now, having said that, all you really are looking for here is molecules that can have unsymmetric or additive dipole moments. Do you guys remember dipole moments? Okay, it's where you have different electronegativities between the two bonds, right? That make the bond polar. Specifically, you're looking for something that could add those up and have those all add up in one direction, right? Okay, so, and not have them actually cancel each other out across. So there's a few different rules that can help you out here. If you have an inversion center, you can't have it. Automatically, inversion center means there's always the same thing on the opposite side every single time, right? Otherwise, it wouldn't be an inversion center. Okay. More than one rotational axis also cannot be polar because, again, if you have more than one axis of rotation, then that means that it can rotate in both of the directions, right? And so you've actually eliminated all your x, y, z coordinates by doing that. Okay. And then the other one would be if you have a dipole, rotational axis, and then a horizontal mirror plane that goes along with it. Because the rotational axis will eliminate one direction which it can do, and the horizontal plane will then eliminate the others, right? Yeah. And so when it comes down to being polar, the only ones that can be polar are just these right here. You'll notice those are the low symmetry ones. Okay? So if you go over to the low symmetry side of that flow chart, C1, CS, Cn, and Cnv. Okay? Those ones can be polar. If it has any higher symmetry than that, it can never be polar.
Sorry, it's saying if an inversion center is present, then it must have a dipole, or
Cannot.
can't have a dipole?
Yeah. Yeah, because that means you have the same group that can be inverted, right? So you'd have a chlorine here, and then on the opposite side, you have to have a chlorine.
Because if it inverts, that just switches in. It's still polar. I'm not polar.
Exactly. So they have to be able to cancel each other out. Yeah. That making sense? Okay. Yeah, I wanted to go back and get more specific. If that's too loud, by the way, if somebody could close that. Otherwise, I'll just shout above them. Okay. I believe we ended here last time, right?
So CS just, what does that mean again? Like C1 and the CV, like CV vertical plane.
So do you have your table, your flow chart in front of you? Okay.
So CS is mirror plane? No symmetry. Or is it improper rotation? It's a reflection.
Here it is. Okay. It's right here. So you have a reflection, mirror plane, but it's not horizontal. Okay.
Okay. So the vertical mirror reflection. Okay.
One of the verticals. Remember, though, that this doesn't have a rotational. So it just has a plane of symmetry. Okay. These typically have things like, for example, this would be like cis-ethene. Okay. Where it has a plane, right? Okay. Oops. Okay, let's see. We're on 40, I believe. Okay, so last time we left off here, and again, this is where we left off with our principal axis. And in these coordinates, we can actually generate matrices. I just want you to understand that these exist and how this connects in, okay? I'm not going to be expecting you to actually be able to solve and generate the complete matrices because I don't believe you guys have had any experience with matrices at all. Is that proper? Is that correct? Okay. Yeah, and it would just take too much time for me to teach you matrices. We wouldn't be able to cover any of the other materials for this course. Or I would have to expect you to learn linear algebra in a week or two, which is seems a little excessive. Okay? Though it is something I myself had to do. So, how much do you want me to expect out of y'all?
Like we're newborn babies.
Newborn babes? Okay. Okay. So what we're actually looking at in these is matrices look like this. Has everybody seen that before? Okay, that's a matrix. Okay, and matrix are designated by an M and then X for times and then N for the other number. So the vertical is the M numbers. That's how tall it is. Okay. And that would be the number of periods if it was a periodic table, or the number of rows, right? Everybody okay with that so far? Okay. And the n number, those are the number of columns. Okay, so if we had a 9 by 9 matrix, we would have 9 numbers coming down, 9 numbers coming across, right? Okay. Okay, so let's say we were trying to pull a number from this. What we would do is we designate that number as typically A, like this italic A looking thing, right? And we put the, again, row first, column second. Okay. And so, for example, 1, 1 would be this one right here. It's the first one here, right? 2, 1, next one. 2, 2 would be this one over here, right? And so then we could pull numbers from this. Right? Now, there's a bunch of different specific matrix maths that have been developed. Your book actually has a boiled down version of it in the appendice at the back, okay? Which has been very specifically created for this use. Now, your book does this in matrices because this is how you would have to generate them if you're not exactly sure what you're going to do with them. And you need to understand them from every single aspect, okay? However, it is fairly challenging for most people, especially if you haven't had linear algebra before and you're not practicing matrices. And I'll be honest, this is something that I don't use a lot outside of computers. So, like, I regularly forget matrix math stuff quite often, okay? I usually have to look back, right? Because this is something that's really, really useful for computers, actually. Like if you do this in Fortran, it's actually a lot easier. Okay, and that's actually why this is really, really good for computers, actually. Because if you're doing calculus, you can do calculus in matrices, and it's a linear process. It's not integrals and all that. It's different. Okay, and so you can actually put a calculus, what would normally be a calculus thing, into a computer as matrices, and it can do that math. Okay? Whereas if you tried to input calculus as is, computers can't really do calculus. The symbols don't mean anything. Okay. So this right here is actually the representations of this information. These are actually matrices, right? Can everybody see those? Okay. And this is actually how they would break apart if you were to do the entire matrix of these right here. Okay? And there's something called great orthogonal theory. That's actually how you break those down. All right? Now, this is where I'm going to sort of cut off and say, undergraduate, really the expectation is point groups, be able to read these point tables that I showed you before, and that's about it, okay? Can you take a molecule, get to its point group, and read the point table well enough to figure out what sort of modes it might have? Okay. Graduate school level, this would be graduate school level where you start breaking down matrices if you go that far. Okay. And this would be a fairly advanced version. This would be like a spectroscopist, which is sort of the mathiest or physiciest of all the chemists. Okay. Okay. Anybody have any questions about that so far? I know I'm trying to skim over the surface.
This one right here, the smaller graph to the left,
Mhm.
with the table, it's just the Z, Y, and X axis is on the left for the rows, right? Is that the
This one?
axis? Yeah.
Yeah.
And then, of course, like the type of modes, like identity and stuff like that. And then the numbers, is that just like,
How it transforms.
okay.
Doesn't transform in any of the directions. This one right here transforms in the Y. This one here transforms in the Y again. This one here transformed in the X as well, though, see? And this one just transformed in the X. Is that making sense? Yeah, those are how they change in those different directions.
Okay.
So the negative one just means
A
that-
transformation.
and the one means
No.
nothing.
Nothing.
At that, on that axis.
Yeah,
Okay.
on that axis. Yeah. Yeah. So for example, in this case, we're doing a spin around one of the axes, right? So one of the axes doesn't transform anything. The other two axes all transform because we spin it around one. Okay. And this one, for example, we do reflections in one axis, right? And so we change only one axis. That making a bit more sense? Okay. Very good. And they can actually, these are the irreducible. We can actually do the reducible representations, which is more specifically how they transform in every possible way. Okay. And those would be more molecular specific. Okay. Whereas this would be the entire point group. They'll work for everything. Okay. So this is actually right here. What is this molecule doing right here? Can anybody tell what's happening to that molecule? Yeah. We're doing rotations, aren't we? See that? Yeah, and that's your proper axis right here, because by convention we set the z-axis to the principal axis. Okay, so we have a nice up and down, right, to work with. And then this is actually the rotational axis of how things spin in space. Okay, so if we set this as z, then we just go an x from that, perpendicular, right? And then that's the rotational x. This is then the rotational y. Okay. Okay, so when we have a molecule, what happens to molecules in space? Can anybody tell me that?
In space,
Yeah, what do they do?
aren't they just continuously rotating?
Yeah, they're always rotating in every direction, right? Yeah. And so typically we're going to have, for most molecules, 3 rotational modes that are always happening, and they're always rotations, right? And this would be the 3 rotational modes. Notice these rotational modes play with these symmetry elements differently, doesn't it? You see that okay? So, depending on how these rotational modes interact with the symmetry elements for that point group, they're going to have different transformations. So, for example, this right here, the E never changes because yeah, it exists. But for example, this one right here, if we do the Z rotation, that's going to change in this one right here, isn't it? Okay. So we would affect our Z rotation by doing this symmetry element. Everybody okay with that so far? Okay. Okay. Now, what else do molecules do? Do they just rotate in place and that's it all the time? What else do they do?
Get attracted to each other.
They get attracted to each other. But what if we just have one molecule? We won't worry about the others. Okay? Get rid of everybody else. Let's just concentrate on one molecule so we can actually make some sense of these things. So is it just frozen in place?
Is it? Oh, never mind.
It does translations, meaning it bounces around. Okay? It moves in the X, it moves in the Y, it moves in the Z, right? Okay. And so that's the other modes we're going to end up having to talk about is the translations. Remember that table I gave you that had the RZ, RX, RYs on it? It also just had Z, X, and Y. And that's it. Same column. Those are translations. It means we're moving in the X, we're moving in the Y, we're moving in the Z. And that affected that symmetry. Okay. Let me ask you about linear molecules. Would a linear molecule have the same rotational?
They have an infinite amount of rotations.
Yeah, so a linear molecule ends up having one less rotational mode that will do anything. Okay? And so one of its rotational modes actually ends up being degenerate, doesn't do anything. And so you actually have one less mode you'd have to accompany with that. Okay? Okay, so this is again your water here. This is the bond vector specifically of how these forces align with the bonds and your E and C. And you can see you can start breaking down every possible aspect of these molecules according to these symmetry elements and how they would affect the symmetry elements, right? We could do orbitals, we can do rotations, we can do bond vectors, we can do translations, we can do, if you vibrate the molecule, how it does. Every single aspect, right? Okay. And so we can actually reflect those within these aspects. I'm not going to end up doing this at all with you guys because it's the matrix stuff. Okay? And I started going through it and went, oh my God, I'm going to kill my students. Okay, so let's talk a little bit about irreducible representations in our characters, okay? So here we have our character table. They're going to have our complete list of irreducible representations. Your book abbreviates them IRR. You have to work with these a lot to have an abbreviation for them, which is just wild. Most people don't bother abbreviating them, okay? So don't try to go up to a chemist and go IRR. They're gonna just look at you. What the fuck? Somebody spent way too much time on this stuff with you. Okay, and so that's what these are right here. They're the irreducible representation. They're as broken down as they can get, and you see we have managed to collapse them down to a single line. Okay. And that's what these always were. Remember this table I'd given you before? And you've been like, what is in that? Yeah, I was waiting for this part to really start talking about it. Okay? Because we still needed some items. Okay, so right here, point group, right? Okay. And then these are going to be your irreducible representations. Right there. This is specifically the Mulliken symbols for those. Schoenflies, point group symbol, right? And then these right here are our operations, right? We have identity, rotations, whatever operations are in that point group. Okay. More symmetry elements, longer the table gets. All right. So this right here is actually your characters for those operators. Again, remember that they're going to be how these things are transforming. Okay. So for example, this right here, we have the E. It transforms in this way. Now note, because we end up with a more complex set of things going on in these irreducible representations, they're not always nicely identified as X, Y, Z. Okay? Because sometimes molecules just don't break down nicely into everything happens in X, Y, and Z, right? They're three-dimensional objects. They can have things in corners. Okay? Okay, so this right here, again, your operations. Note the operations in these tables typically actually have your Z X and Y. This is to help you out. Okay? So for example, your C2 ends up being your Z-axis, isn't it? And so it's just straight up your Z-axis, isn't it? Okay, and then these happen within those axes. This is the X Z-axis. This is the YZ axis that you have this reflection going along. Okay, so we got ding, ding. Everybody okay with that so far? Okay. This right here is your rotations and translations. All right, so for example, this A1 here has your translation in it. It moves in the Z-axis. So we jerk it upwards. Okay? Whoosh. It's flying up. This one just rotates in the Z-axis. That's the only motion of those it has. Okay, this right here represents your moving in the X-axis and the rotation in your Y-axis. That okay for everybody? And this is how it affects those symmetry elements. Right. Okay, and so these right here are going to be where you have the basis functions for these things. And these basis functions are going to be where you solve these out and exactly how they affect it, okay? I'm not going to go through how you get these, but that's what you read off of it, right? Specifically, they're very important for spectroscopy, okay? So this actually is what tells you if something is Raman or IR active, this part of the table right here, okay? So will it show up in this type of spectroscopy? Okay, so these are all the rules to figure these out. If you ever end up, you don't need to write out all these because I'm not going to actually have you go through and actually create irreducible representations. Okay? That takes some matrix math that I'm just not going to make you guys learn all that. And I'm going to cut this part out, I guess. Let's have you identify all the symmetry operations present in the molecule for trans-dichloroethylene. And you can get the molecular point group. And we can't really do the rest of those without going full-on matrix math. So, did you guys want kits? Did you all want to grab kits?
Might as well.
Okay. Yeah, go ahead and go through and grab a kit.
For the point group, we need the flow chart, right?
Yes. Mm-hmm. Did you ever get your book?
Not yet.
We're gonna hit midterms before book.
Probably.
Jeez.
Yeah. Don't those will just like pay me tutors. Alright.
What are we tutoring?
Science
lab. Gen chem, whatever I know in organic. Pretty much.
Cool.
Maybe some inorganic.
If you get stuck, let me know. Yeah. Yeah, maybe we could have some inorganic tutoring.
Yeah.
That'd be good.
I can do your nuclear binding energy.
Well, by the time you get done with these, you'll be able to tutor this. Make your nice molecules. make sure you get the trans. And did everybody figure out how you do the double bonds? So you take the long one and you connect it to 2 parts. So 2 of those long ones. I didn't do it because it was would cause problems.
Oh, I'm just gonna,
Oh, you didn't get carbon, but that's okay.
I didn't, I only have one.
Here, you can use
My kids are just like
Okay.
clearing out all the cotton.
Oh,
Oh,
very nice.
so this is the transformation? Wait, that's
That'd be 6.
6. There you go. Oh, okay.
Oh, yeah.
Yeah, wow. I'm not really gonna have to take all those kits down and get them reorganized, aren't I? Yeah, it's really bad. So don't forget to rotate these things around your hands before you start assigning things. Mm-hmm.
I actually have a question.
Yeah, of course.
So with proper rotation, I'm just confused on all this stuff. So with proper rotation, how do I know that it has like this way and that way and that way? Does that make sense?
So you put it in rotate, see if you can line up. So this one right here, if you try to rotate it like this, it's not saying.
So I remember you said like in that one class when you rotated it the same as you started it. Okay, so I'm just trying to find ways that it can just like that way.
Close your eyes, rotate it. Same. I mean, but
This one, not a proper rotation, right? Yeah.
Yeah, because it's pointing a different way. Okay.
But if you put your axis right through that double bond there, right? It's like a 2-blade propeller, doesn't it?
Yeah.
A weed.
Mhm.
Whack, whack, whack.
I guess
And so you got C2 right there.
And it's C2 because as of now, we only have one axis.
So the 2 represents 360 divided by 2.
360.
So I do a
Oh,
100 degrees,
okay.
and that gives me my deal, right?
Okay.
If I had something that I could do 4 times in 360, it'd be C4.
Can I want to change the model, but I just want to make sure I get this concept right. So if it was like this,
Mm-hmm.
wait, no, I got it. And I did it like that,
You got it.
would that be C2 again?
It would.
Because- Okay,
That'd be another C2.
and then okay, and then I did it that way. But if I go that way, it's not the same. Okay,
Right, but that would be an improper rotation if you did the rest of it.
okay.
So if you go like that,
That's good to proper, which is that SM.
you're being improper.
And would it be S2?
Sorry.
Would it be S2 because it's another 180?
Yes. Now keep in mind that improper rotations end up being the same thing as a reflection.
As a reflection.
If it's a C, if it's an S2.
Okay, got it. So just the like, so the C6, that would be 360 divided by 6. Which is, I don't know how many years it is. Okay. So 60? Okay. And then C3 would be 120? Okay, perfect. I was very confused.
You got
Thank
Why
you.
do we always look at the mouse in like a flat 2D? I know it's 3D, but like I thought, why am I looking at it like that and not like this? Why are, like what? Because now if I rotate it, I mean, or I could just like, here, and like it's the same thing too,
You have to go a bit further.
right? Like that, yeah. So, and then
Yeah.
it's a 180, but.
It's just harder for people to see these usually.
Yeah, so that's
If
why
I show it to you
do
like that.
Okay,
Yeah.
so I can even look at it like an angle like that.
Yeah.
Okay.
Oh, yeah.
And then
axis is that C2 rotation. That's the principal axis.
Oh, yeah, okay.
It's your highest rotation, right?
Yes.
So automatically, that's your Z-axis right there,
Mhm.
principal axis.
That's a vertical
If
inflection.
you had a higher rotation, that would be,
Okay.
so like this C6, that was your principal axis there.
Oh, okay, so if I had like a C3 and C4, I don't know if that's possible. The C4 would be the principal axis.
Exactly.
Okay.
Yeah, whatever is your highest rotation.
Okay. Got it.
And that's also gets set to your Z. And that's typically why we end up saying things like that. That's why, like, automatically when I took it from you, I did this.
Yeah.
'Cause
Because that's where you flipped it around.
that's my Z, isn't it?
Yeah.
Yeah. And so, like, when I'm showing you things, I typically orient the Z-axis towards you,
Mhm.
so you can see down the axis.
Mhm. Okay.
And what we're looking at here then is vertical is going to be anything that goes parallel through that axis, right?
Mhm.
Okay. Horizontal will be anything perpendicular to the axis.
Yeah. So this molecule does have the horizontal?
Yeah.
Okay. So then
Horizontals are much more common
Mhm.
than verticals.
And so would this one have a vertical? So a vertical would go this way?
It would.
And so in order for it to be a reflection, does this one have to be on that side
It
then?
would.
Oh,
Yeah.
so this one will not have a
This
vertical.
one will not.
Okay.
Yeah, you directed, didn't you?
I'm slowly getting there.
You got it, you got it.
Improper rotation would just be I can rotate it 90 and then flip it and
Exactly. Be careful though for the improper rotations, because the S1 and S2s are not unique.
Right. Oh yeah, that's right. Because if you do,
Yeah, so the S's, improper rotations, they're the buggers that tend to catch people, because the S1 identity, right, S2 reflection.
So with the improper rotation, to figure that out, it says it's a rotation and a reflection. So would you rotate it the amount of times you have your proper rotation?
Typically, those will line up,
So okay, you.
but that's not necessary. So you can have a improper rotation
Mhm.
and no C2, no C,
Oh, okay.
no proper rotations.
Okay.
but what I just did was an S2, so it's not really significant.
Exactly.
Because I rotated 90 and then only reflected it.
Yeah, so if you take your molecule
Right,
and do the same sort of thing, you could have seen that.
It just does, yeah.
Yeah. Like you could.
So if it was significant, I'd have to do like a 180 rotation and then another 40.
You would have to do something higher than a 180.
Higher than a 180.
So like a 120 would work, 60 would work, any higher symmetry down would work.
That rotation.
But the S1 and S2s just ignore.
C2.
Because you're actually taking care of all of the other symmetry operations.
Good.
And so the last thing you should look at is also the inversions.
Inversions. Okay. So
And you pull everything past. Like the opposite side.
so wait.
Just goes from F to C.
Oh, okay,
Take
so
this
F.
corner and go-
Every coordinate just gets flipped negative.
So that. Sorry.
So, this would go here, this one would go here, right? So like this would be positive X.
Mhm.
So make it X, right?
Mhm. Yeah.
And you, yeah, you can do, that's actually,
Oh, so that's the inversion?
yeah, that was that improper rotation, I
Can you show me how you did the proper?
think. So this is an
Improper.
inversion
Okay.
and an improper rotation.
Because.
Because I'm changing all of the X, Y, and Z to the opposites.
Can I try it just to make sure I got the
Mhm.
So you went like this. You went like this.
Hmm?
Then you flipped it.
Inversions.
Oh.
The improper is rotation and reflection.
The rotation
And
there.
reflection. Yeah.
This is the rotation.
Reflection.
That was it.
Rotation. Rotation.
Rotation. So.
So rotation always has to maintain what makes that inversion is because this is actually taking our rotation around the z-axis, right? Changes all the other coordinates with z. And then when we flip this, we flip the z. See that? And so we flipped all coordinates that are negatives.
Okay.
So be
I'm
like a first grader.
I know.
I know, right?
I feel like I'm back in like high school chemistry.
Yeah.
You're just learning everything. You're just like, whoa.
Yeah, this is, the funny part is, this is like super profound, by the way. Oh, by the way, you know you can get all the answers for that later part from that spectroscopy book I gave you?
Okay.
You literally could have just done all this stuff without any matrix math, simple algebraic formulas with these rotational things I've told you guys,
Right.
if you just use those tables in that spectroscopy book.
Okay.
What's the point of this if molecules are always like moving in space?
That's actually why we do this. So we're actually building up, notice all of these are internal
Right.
to the molecule, right? So these symmetry elements are the same axis z, no matter which direction I'm pointing this now, right?
Right.
So I have built an internal categorization of this molecule that's always true. It doesn't matter if it's bouncing 100 million miles a second. It doesn't matter. It's,
And that's just to like identify. This is more used for like identifying really complicated molecules.
oh no, even the simple things. Yeah, this is used to identify like that. For example, and what causes more global warming? What's the leading cause of global warming?
CO2 emissions.
Nope. Nope, less than 1/3 of the global warming effect is CO2 emissions. What causes 2/3 of global warming effect?
You know, just.
Yeah. Yeah, you guys thought you knew something about global warming, didn't you? Water. Water. And that's because CO2 only has 3 significant infrared bands. Only 2 really that make a real big difference. And so it absorbs a very small amount of infrared light, actually. And water, on the other hand, has many more bands. What is that?
My water has.
Why would water have more bands?
It's
Polar.
Yes, it's polar, or another way is the symmetry group.
right.
That symmetry character tables I'm teaching you guys to read,
Right.
that's actually what determines how many infrared bands there are. That's what determines that CO2 has less infrared active bands, so it absorbs less infrared light, which is what we're recycling, global warming, and the greenhouse effect. And so, yeah, water is 2/3 the greenhouse effect, the global warming effect, because it absorbs many more infrared bands, has many more modes that are infrared active within what's called the infrared window. It's the window that doesn't normally get reused.
So are you saying global warming is because of the fact that we emit water?
So the greenhouse effect, which increasing greenhouse effect is global warming,
Right.
is because more water is going in the atmosphere. The problem being we can't actually control water going in the atmosphere, and so we ignore it and just concentrate on CO2, which we have a little bit more control of. This is also why like methane
Right.
is actually 30 times the effect per ton that CO2 is.
Right.
Because it has more infrared modes.
But do you think more chemicals that we emit as like humans, once they reach the atmosphere, do they separate into like water molecules?
Oh, we have tremendous, yes.
Okay.
You have to remember like combustion,
Right.
which happens naturally, spontaneously to all like methane, also generates water. It's one of the problems.
Right.
And there's also another effect that's happening where we're creating water pockets in certain areas that's actually changing global warming. This is why you can't just like do a real quick back of the envelope calculation and be like, this is what the predictions are. If you ever look at the prediction models,
Yeah.
there's dozens of them because there's a lot of factors that come into play actually. But yeah, 2/3 of the effect is water. Yeah, in the atmosphere. The problem being that water actually is mostly dependent on temperature and bodies of water. So, you guys know what humidity is?
The worst.
So humidity is actually at 100% scale, right? What's 100% humidity?
You're underwater, right?
No,
No?
no, not all. 100% humidity is the maximum amount of dissolved water that could go into the air for that given temperature.
Oh.
Yeah. After that, you would actually precipitate out, and then you would get beyond 100%. Remember, pure liquids don't go into the concentration calculations. So, like, yeah, you were surprised, right? This stuff I'm teaching you guys is a whole way to understand the world. Okay, folks, let's go ahead and move on to the next part. So, what are all the symmetry operations present in this molecule?
Activity.
Ooh, you were so clever.
It exists.
I'm gonna have to get everybody else. Is gonna have to do the other ones now.
Yeah, there we go.
And you got. See, you were. Okay, so what's the next operation?
An inversion.
We have an inversion. Yep. Any more?
Proper rotation.
Proper rotation. Oh, you took one of the other people's. Is there any other ones?
Wait, where's the proper rotation? Is that this one?
Yeah. You got it. Okay. You sure there's not another one?
Inversion, proper rotation.
Pretty sure.
Okay. This thing looks really flat to me.
Right.
Could there be maybe a plane of symmetry?
There's definitely a symmetry.
Mm-hmm. What operation is that called? Plane of symmetries are like mirrors, right? What do mirrors do?
Reflection. That's a horizontal plane, right?
Yeah.
Okay.
So would that be the
Horizontal reflection, yeah.
It does have reflection. Yes.
Reflection H.
It just doesn't have an improper rotation because it's an S2.
Yeah. Yes. Yeah, your S1 and S2 you guys have already done.
Just
Yeah.
throw them out. Yeah.
and it doesn't have a reflection from the vertical?
No. Because that would actually have to line up with your, yeah. So if you try to line it up with your axis, exactly.
But then the horizontal reflection is literally
Right through the plane of the molecule, right? Yeah. Anytime you have something flat, horizontal reflections are probably what you're going to be dealing with.
So you see everything, you just don't see the horizontal. Is that looking at it like this or like this?
So look through your axis.
Like this one?
So your axis is right here, right? So you go down that,
Splitting the bottom.
and this would be perpendicular to it. Making sense?
Yeah.
So horizontal is always perpendicular to your principal axis.
Is our principal axis or sections up? Okay.
And then vertical is always where it lines up with it. That makes sense? Yeah.
So then the bond, that's just this one then.
Mm-hmm.
I thought that was the C2.
That is C2. That's your principal axis.
Yeah.
That proper rotation is your highest rotation, is always your principal axis, and your speed horizontal.
Got it.
And so this axis comes through here. That's your principal axis and z coordinate. The reflection that goes perpendicular to that, and then the y is your reflection H, the horizontal. Because remember, this defines your principal axis. Because it tells you up and down, and this is the z axis.
So
So it doesn't have to be like,
Y-axis.
it doesn't have to reflect to be the same. It can reflect like this.
It doesn't.
That's not a
I looked at
reflection.
mine like this.
Yeah, so the reflection here, is gonna be that you actually have
You reflect
it the same deal. Another way to do a reflection is
You do
like
like that.
Yeah. Yeah, that's like the way I'm thinking of it, but then it's
So-
the same page. So I get that, that's the principle.
So see that we'd actually split this point, right? We'd split this part in half.
You got like.
So we'd split all of
Say
this.
we have a mirror right here.
Can you see that part?
Yeah.
So, like, if we try to go up for this and down for this, right? Well, it's the same.
It's just like if you were
Okay.
coming from the mirror, putting that right here.
And so we've done reflections, now all
If you
these still looks exact same as that.
Well, we didn't do the double.
It would look like the same as that.
We did.
Put it in the mirror. If you
It's
put
the
it,
exact same.
if you, we
Yeah,
had a mirror.
like these not rotates
the
as
same,
connected to the
say
double
put a
bar.
mirror.
Okay, so this can't rotate
The
along.
camera.
That's confirmation, so totally different thing.
Okay.
Okay?
The camera.
So you got your, principal axis.
Let's use your.
Well, the principal axis is just the
This
first
mirror,
right?
Like I
So
said,
then, like this is the
imagine
principal
you
axis,
took
going
this,
up and down there.
put it in the
and
bathroom
then
horizontal, put it up to your bathroom mirror. It's
Because it's just like,
Yeah,
so it's through here.
because then when we rotate it like that, that's the same.
Exactly. Exactly.
Okay.
And so now we go horizontal, typically it's easier for people to see it as a mirror plane. That it's just a mirror reflection both sides, right?
Oh, so because this is now,
So
on
let's just,
because it's trans, it has
you
the.
have a mirror on the wall.
That actually would have it both ways. It actually doesn't matter because it's nice to have one that's this way trans. So these both have horizontal mirror planes either way. And that's because they're flat. So automatically they always end up with
Horizontal
planar
mirror
symmetry.
is always perfect.
So pretty much it's always like every single thing is kind of gonna have horizontal.
Oh, no, you will have ones that won't have
You do
horizontal.
one horizontal mirror plane in a molecule.
So there's no actual, like we're not moving the model.
So you
in
can
any
do
way.
it if you want to do it.
Horizontal.
So how you would do this is you would spin
Mhm.
and then flip.
I thought that was the inversion.
Yeah, so this one's difficult to do physically.
Okay.
Yeah. And so what you'd end up doing is, again, you basically have to just rotate it completely back into position.
But, okay, isn't that also the inversion?
Because a plane of symmetry or reflection doesn't actually need to, in this case, because it's flat, again, you're actually moving these things, the lower half up instead of
It's called a mirror plane.
Okay.
like we're actually splitting atoms here to do this. So see, you're cutting these in half, right?
And then they
And
just.
so we're flipping upper half and lower half. We're literally going there.
So how would we be able to know if we wouldn't be able to do that then? Like, why wouldn't we always just be able to do that?
Okay, so like, let's get something. I'd have to think of something, an example of not. But, oh, here, this will be easy. Where's my phone? Think about a triple bond, linear, right? Okay, we can have one that has different things like a sine, okay? So it's linear, we have an infinite rotation around, right? But if we try to do a horizontal plane of reflection, we have a C, an NC image, right? And so they wouldn't be the
That's
same.
So now we get horizontal.
So we'd only have vertical planes.
We're just gonna say which way do you want.
You guys wanna make that real quick, and I can show you?
Just the vertical side is going down, right? Split it, right? Sense of size. This is the bond. So we start with to see if you have proper rotation. It's gonna be symmetric as well. This is linear. It's not gonna be like,
And so this would be sine, right?
Yeah.
And so principal axis right down in the center,
You see
right?
how there's gonna be a reflection that's gonna be the same.
So now we look at this, it would have
That
vertical,
means it has a
Yeah.
vertical reflection.
right?
Mm-hmm.
Okay,
Because
now
it'll
let's
line
compare
up the
that
principal
horizontally.
axis.
So you get a
With each
horizontal
bound.
reflection.
No, because that's.
No, just period. Because remember, this is not actually,
Yeah, the bounds are just, yeah.
Your proper
like,
rotation.
this is just not
Just do it
tremendously.
here, right?
Yeah, through proper rotation.
But, and that's actually why that first time I did these, I didn't actually make the
But
triple
this
bonds.
isn't the same.
And then a horizontal rotation is on
But
Okay,
this is
and
the
so if we
same.
tried to do it this way, there's no place
If you
here
reflect it,
where it'd be the
like,
same on both
the-
sides, right?
reflect it, it's gonna stay the same.
Yeah. And so we don't have
What's on the
horizontal.
bottom is not what's on the top.
Right, but when you reflect it, it's
And on this one, when we do it, we can get it the same on both sides.
Yeah, so the easiest way is just to look for a mirror, where it's the same on both sides, okay? Because this is one where if it's flat, trying to change it
I'm also trying to
to
understand.
match up is going to end up looking like an inversion, okay? Because in reality, what you're doing is you're taking this piece right here, and you're actually one like,
But you're just doing that with every piece, like we're making the up, down,
And then
down.
the mirror is
Exactly.
gonna be.
because we're actually splitting out the atoms.
And
We're not like.
Think about it, think about it, think about it, think
And
about
so
it.
we're not even
Right,
turning
we
this
cut
like
them
this,
all
'cause
to
that's
half.
how we-
This is the most
Exactly.
original.
Yeah, principal axis is
Now
always
imagine
drop
a
down.
saw, and I just cut this in
Always
half,
your
we're only looking at.
And doing that, there's no way
Got
to
it?
flip
Okay,
the
so now we're only looking at the top.
Well, although,
Mm-hmm.
So
if we
let's say I
do
put
it
a
like
mirror
that,
down.
with this up, down, wouldn't that just
It's
change
gonna
the
look like that.
direction?
Put a mirror right here,
That's
it's gonna
changed the
look
whole
just
thing,
like
right?
this, isn't it?
So if we did this, if we tried to do this as our horizontal, reflection, this would come up here,
Oh,
same distance.
Look at that.
This would go down there, same distance, right?
That's a reflection, yeah.
That's rotations, but.
Yes. Mhm. That's always your highest order of C.
and that's because this can just go like
Right.
this.
Exactly. And that's infinite.
Okay, so like same here, I'm just gonna say this is cut them in half, and like bring it up like that.
So
Maybe
this
it's-
part is
okay.
broken, but this one is cut in half.
Yeah, now you're looking for.
I guess you could do it too.
Yeah.
There you go. Yeah, there you go.
Okay, yeah. What I was thinking was, but at first I was thinking like if we did the mirror, it had to be the same, but never mind.
Oh, no,
Yeah.
I mean,
Makes sense now.
yes,
That's-
but, it is the mirror plane,
Because it's horizontal.
but yeah, it's, you were mirroring it on here,
Yeah.
which is not the issue.
Because you can see the yellow.
So this is that mirror
So
with
let's
no
do-
reflection back over, right?
Yeah, linear is just gonna be
And so that one,
all the reflections.
non-reflection.
And, we were just talking about reflections, well, I had to show on the reflection of the screen, that worked. But,
Yeah.
like, as far as being unsymmetric, like, is there a molecule that doesn't have a reflection, like, let's say this, if we were to do a horizontal, and I just go up to this reflection, like, it's not gonna be symmetrical and everything.
Oh, okay, yeah, it's
Yeah.
the reflection of,
Yeah.
okay.
And then if we were to do a vertical reflection, that we would have the, yes, okay, but to deem a reflection, do you only have to have either a vertical or horizontal?
No, you can have both.
You can, or you can have one.
So you can have a reflection H or reflection
V.
B, you
Right.
can have a
Just
reflection
one.
D,
D.
where it doesn't actually line up with either, way for an axis, it's like, this is your axis.
Right.
So it's not horizontal, not vertical, right?
Yeah.
Diagonal.
Right, diagonal. Okay. Alright. So most molecules, or almost all molecules, have a reflection somehow or another.
So there are ones, again, that's that character table. If you look at that character table, you'll
It'll
see that
s-
there's point groups that don't have those.
They'll have them in the transformation. Okay.
Yeah. Now, there is a certain level of symmetry that precludes and makes those necessary.
Right.
Like if you have a certain number of axes that you can do rotations or a certain number of C value, you'll start getting these other symmetry ions that also have to be true.
I'm
Yeah.
sorry, we were.
No, you're good.
Sorry, I just,
Mhm.
I think the horizontal reflection is really,
Okay.
so how did you know that this right there was?
So this one has a vertical.
Mm-hmm,
So this is your axis, right?
mm-hmm,
Right.
Right.
that's a
One
vertical.
it a vertical because it intercepts the principal axis.
Mhm.
And then horizontal would have to go this way.
Yes.
And so this is actually, remember that they also came up independently as one that doesn't have horizontal. I usually use linear ones because that's easier for me to figure out.
Okay, sorry.
No, you're good. And so for example here.
Wow.
So this one right here,
Mhm.
like if you were to try to go anywhere here and then reflect downwards,
Yeah.
well, that's not the same as that.
But you reflect. Wait.
Okay,
So you're,
so look at it, close your eyes.
Oh,
And then open
because
them.
it's at the bottom and not
Yeah,
on top.
exactly.
and so it's different now, isn't it?
Yeah.
So then with this one though, when you put it
Cut it down.
in half,
That one would be
so
different.
this one is reflecting and it's on the same side.
So this one right here, this is actually your axis right here.
The box.
Yes.
Okay.
Okay. And so right here, if we go through here, can you see that this is the same on both sides?
So it's like this.
Yeah, it's this plane that the molecules in.
Okay.
It's actually how you'd write it on paper, right?
Okay.
Your paper would actually be your mirror plane,
Mhm.
and so that would be your reflection. This one's a little bit more difficult. You can't really do an operation here
Mhm.
because you'd actually be taking these and you'd be rotating them
Okay.
because you're going through atoms, right?
Yeah.
So the easiest way to look at these is actually just to look for planes, which it's symmetric across.
Okay.
You know, like you look at plane of symmetry, plane of symmetry,
Mhm.
plane of symmetry, right?
Okay.
That's a reflection.
Okay.
Okay? And you instinctively actually do a plane of symmetry because that's how we judge people's
Mhm.
facial features. So
Okay.
that's usually instinctively the easier ones to get is to take a plane of symmetry.
Mhm.
Those are reflections.
Because I think I'm thinking of a reflection as a flip. Do you think that's what's kind of like missing?
Yeah,
here?
it's not a
Because I think I'm thinking like, okay, a reflection, like if this is the mirror, like, flip, it's
yeah.
Same.
So it can sometimes be three. Okay. So for this case, because of the shape of it, a flip does do a reflection.
uh-huh.
But the problem is when you start dissecting through
Mhm.
all the atoms in the molecule,
Mhm.
what you're actually doing is you're taking the top of an atom
Mhm.
and you're moving it to the bottom. And you're doing that for all. Okay. And so that actually is what the
Oh,
reflection is.
so like for this one, the reflection, you're flipping that, so then are you taking this one off, and putting it at the bottom?
So in this case, a reflection, again, we would be
Sorry.
taking this. Remember, it's this plane, right?
Oh, this one, okay.
Yeah. This is not a reflection. Not a mirror. Okay? So this is the plane of the reflection.
That's the
What's my time, by the way? Open? Oh,
I'm sorry.
I'm gonna have to pretty soon because I got another class after this. Okay, so what we need to look for is you'd actually be taking this, and this is your top now,
Mhm.
and you'd be rotating it like that.
Okay.
Because it's going through your atoms.
Okay.
It was only happenstance that you could flip it,
Mhm.
and it worked.
And it's just like, if you were to put an object in front of a mirror, it would still be the same size.
Exactly. Yeah. This is actually a literal reflection,
Mhm.
as in what
Yeah.
it's supposed to be.
So that would be a vertical one. Right?
Yes. Because it passes through the principal axis.
Yeah.
Mhm.
And you can help yourself out by always leaving your principal axis in the Z.
In the Z, okay.
So point out.
Okay. And then your horizontal, would you turn the horizontal so you can,
So this would still be vertical.
okay,
We've flipped our Z axis, so we're just,
yeah,
sorry.
Right. And if you just think about it, if you just turn
Horizontal
it
with
like
that, it's up like that.
so that would be when
one's pointing away from me, one's pointing towards me.
Aaron, good.
Okay, I think I'm slowly starting to
Very
get
nice.
this.
Peter.
Okay.
Yep. So this is a very practice-dependent thing, because remember, you're having to exercise a part of your brain that you may not use a whole lot. Okay? Modern day humans, this is part of the brain that we don't get a lot of practice on a daily basis. Funny enough, there's certain types of activities in sports you actually get a lot of practice on. So, in video games, you get a lot of practice in this one. Yeah, just kind of fun. Anyways, okay, did we kind of all get together on that? Right. So if we don't have Thursday, you'll have to cover the rest of the material probably on you guys' own, okay? Okay. And that's the spectroscopy portion.
We should have Thursday. It's only gonna snow for like 3 hours tonight.
Yeah, we'll see what happens. Like, they cancel things for the drop of a hat. The problem is it's going to snow and it's going to be cold.
Yeah, it's gonna freeze like more Thursday
If
Yeah.
we just salt the roads now, it'll be fine. Like the last snowstorm we had, they salted the roads like 2 days before.
Yeah.
I don't know.
I don't know what to tell you. Yeah. Anyways, if you have questions, please ask. And practice, practice, practice.
What are the chances that I can
Borrow the kit. Sign a piece of paper for me. Okay? Yeah, you guys just all get a piece of paper, put your names to it. Hey, I checked out a kit.
If we get kits and stuff, would we be able to use them for like the tests and stuff?
Yes. Yeah, I'd be willing to allow that. Yeah.
I'm sorry, the tests are not, the test isn't open
No.
now. Okay.
What if we all just pitched in a buy you lunch then?
Not gonna help.
And you know what? Yeah. You know.
Yeah. Okay. We'll call that, I guess, a day because I only have 1 minute left. I don't think there's nothing I can do in 1 minute. That's not what we did, right? Okay.